So in these next 2 weeks, or today and next week, we're going to be looking at stochastic optimal control problems in continuous time and continuous state space. So last week we looked at the deterministic case, and now we're going to be looking at the case where there is some uncertainty about where we're going to land, where our next state is going to be. There's some uncertainty built into the dynamics. The goal is to, and also bear with me, this is my first time trying to do this style presentation with the tablet, so hopefully everything goes smoothly. My name is Andrew, by the way, and I'm a third-year applied math PhD student. So the goal is to eventually look at this paper here. Okay. This paper here, this Kaplan paper. There's some very neat mathematically satisfying tricks that are employed in this paper. But in order to get there, we're going to look at some, I would say, fairly basic, maybe underwhelming examples of the deterministic case and then the stochastic case. But hopefully even these simple examples give you some intuition about the Hamilton-Jacobi-Bellman equation and optimal control. So yeah, so we're trying to work towards this drunken spider problem where you have some spider that there's uncertainty in its steps. It follows a bit of a random walk, a slightly random walk. And it's trying not to fall into the lake where there's an infinite penalty for doing so. And then it's a question of does it go across this bridge where, because the bridge is so narrow, there's a good likelihood that it might fall off and suffer this infinite cost? Or does it try to go around the outside, which is going to take longer, but in that way, it can avoid the lake and not fall in. So this is the kind of style problem that we're trying to build towards. Okay, so the first place to start is to review the Hamilton-Jacobi-Bellman equations. So what is the main idea behind the HJB? Okay, so what I'm drawing here is the sort of domain that you're going to see a lot in today because we're looking at a single state variable system. So that's going to be this X, just a 1D continuous variable. So I've drawn it on a truncated domain, but this domain in the case that we're going to be looking at is going to be infinite. And then we're looking at time. So we're trying to minimize the cost to get to this terminal state, capital T over here. And maybe so we have some initial condition, x0, and then we're trying to find a trajectory that's going to minimize the cost that we accrue in getting to time t, right? So this might be a cost with regards to the final state that we reach. It might be a cost on the amount of control that we exert to get to that final state. It might be some state-dependent costs at some other point on this domain other than the final state. And maybe the naive way that we could try to solve this problem is just try a bunch of different control policies, right? And then we can evaluate each one of these paths that we take. Let's say a single path, maybe we denote it as some function, or we don't use A, let's use let me use my eraser. Okay. 1 second. Okay. Okay. We want to call our control variable U, and we just try a bunch of policies, U1 of T, U2 of T, and so on. So here we're just trying things and seeing, what has the minimal cost. So we would minimize over all these different U, some total cost on these, something like this, right? That's naively maybe how we would solve this problem. But there are some difficulties there. I mean, these control paths, these control trajectories that we can take, I mean, that's a very large dimensional, high dimensional space of possibilities. If we're looking at the discrete case, this suffers from like combinatoric explosion, right? I take, step 1 in the first case, but then step 2, there's another possibility there. So this whole thing kind of blows up combinatorically. But what the HJB allows us to do is if we're given an optimization problem with a certain type of structure. So I think generally we can say something like 0t some cost function that's dependent on u x t, and then plus some terminal cost. Let's just say my notation might not be perfect here, but let's say like some cost. All right, so this is over dt and then dt, and then some terminal costs, let's say xt. Maybe let's just leave it there. If we have something like this, so what are we doing? We're saying that we can represent our cost as a sum. It might be an infinite sum, an integral, but we can represent it as a sum. So each step is sort of independent of the steps that come before it. I'll be a little bit more clear with that in a second. But so if we have a problem that has this sort of structure, and this is not every single problem, right? If we're trying to minimize our excursion x, we're trying to find a path that has like minimal excursion over all the x's. That is not something that we can evaluate locally. We have to kind of consider the entire path in order to minimize that excursion. So this is not every single optimization problem, but there's a large class of optimization problems, and maybe we can approximate that problem I just mentioned with a problem that looks like this. But if we have a problem that looks like this, I think the term that gets used is Bellman optimality, right? This problem has a Bellman optimality, or Bellman's principle, I guess, is another term for this. Or I think more from the computer science side, you would call this, you'd say this has optimal substructure. I think all those things are kind of the same, which means that we can solve this problem recursively. And what we do is we know what our cost is going to be at the end, right? We have some function, cx of t, cx of t, capital T, at the end. And we just want to take a step back and ask the question, if we took the optimal step to the terminal state, if we took our, the best possible step that we could towards that terminal state, what is going to be our cost over here? And we're going to call that function vxt, right? So it doesn't depend on the control variable. It is a function of just the state and just the time. It's just a function of this point in the domain. And we can do this recursively and go all the way back to our initial conditions by solving a particular problem, which we know is the HJB equations. And what we've done is we've turned this problem, because it has optimal substructure, and because we're able to do this, we've turned this problem of evaluating paths or evaluating trajectories into a problem of evaluating states. So we've kind of reduced the dimensionality of this problem. That's one good reason to use the Hamilton-Jacobi-Bellman equations. We might see a little bit more about that later. So hopefully that's clear. If there are any questions about that, I'd be happy to answer them. I'm just trying to motivate two things: why we care about the HJB and why we solve this thing backwards in time. And it's because we have our terminal conditions and we need to find the sort of the optimal, the cost of the optimal policy for every state prior to that terminal state. I'm kind of using state and time interchangeably, but hopefully you're able to parse what I mean. Okay, so our HJB equations, actually, I'm going to write it in this form. This might look slightly unfamiliar based on what we saw last week, but our HJB equations, let's write time dependence as well. They look like this, and I haven't said what A is, and that's what we need to talk about. But we understand that this is a PDE, so this A is going to be a differential operator. Now I'll talk about it in a second. And then this cost is just a function on X, U, and T. And the kind of thing that makes this an unusual PDE is our first step is we need to minimize over U. So what this is doing is basically saying, what is going to be my optimal cost at this current state? That's what this equation defines. The minimum U is defining that optimality, taking the optimal U. Okay, so let's talk about what this A is. So hopefully this is clear, but it's going to be useful when we go to the stochastic case. But it might seem a little bit strange at first. Oh, and also I should say that we need to add a boundary condition, an initial condition, or rather a terminal condition to this problem as well. So generally we're going to have some Vx t is equal to some phi of x. This is our terminal cost, right? Okay, so what is A? A is given by our dynamics, right? So there is our system that we're trying to control has some dynamics, right? So generally we can write that our dynamics, if it's governed by an ODE, we can say f of x ut. So our control comes into this dynamics. That's the thing we're trying to control, are the dynamics. And this A is coming from these dynamics. So hopefully this example that I'm about to give is instructive, but we'll see. So let's say I have some function v of x, and so this is x down here, and then this is v, right? And let's say that my dynamics are that the x is changing, right? I have x sub t is equal to some initial x0 plus some bt. So what's happening is that I have some x0, and then this thing is translating at a constant speed across. And we can see that this is going to change my value of v, right? Here, v is up here. And then as x changes and I go over here, then I have a lower v. And the question is, can I write an equation where instead of changing my x, what I do instead is I change my v. So can I find a time-dependent v where I keep my x fixed, but it has the same outcome, it has the same result as if I were changing my x. So is that clear? So my x is sliding across, and the question is, okay, now let's keep my x fixed. X is not going to change, and instead what's going to happen is my v is going to change. And in fact, what v is going to do is it's going to slide to the left, right? Because if this was my initial evaluation, I want my v to change in a way that it's like I'm evaluating it over here. So my v is going to slide to the left. And there is so if you're familiar with PDEs a little bit, this might look like an advection equation where something is just translating and it's not changing form. So we can write that. I'm going to write it like this. This equation tells me how I can change my v so that I get that same output. And this thing here, it's kind of a funny thing that I've created right here, but this is what I'm going to call an infinitesimal generator. So it tells me how I need to change my v instantly in order to get it to behave as it would if x was instead changing, but I'm keeping x fixed. And I'm not sure if people in this room are familiar with it, but this might remind you of like fluid mechanics, where we're trying to turn a statement about fluid particles into a statement about coordinates in space. Yeah, Ben.
So is A, like you have an equality here, is A just the derivative operator, or is it like
So if I want,
the, like,
yeah, if I
like,
wanted
is it you give input a time and output B at that time?
if I wanted to define it formally, it's going to be something like this.
Right, but I think it was like essentially like a, well, like, is it a semigroup of operators?
Is
Is
it?
that what you're
Uh,
like,
yes, I
or like,
believe. I think you should take
like,
this really and it's going to matter in the stochastic case. But you should take this as like the 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 left hand or right hand limit, I guess, as dt goes to zero. Um, this is the formal definition. Oops.
wait, this equality you have here is not really equality. It's associated with this. It's a generator.
It's like I want to define it this way, but I can't. It's very hard to make dots on this tablet, so I'm not doing the dot equals the like colon equals notation. Am I understanding your question?
I'm just like this notation here seems to suggest that A is the derivative with respect to T operator, and I don't think that's what you mean. So,
Yeah, let's say it's not. I'm being a little bit formal. I'm not being exact because it's not partial t with respect to v, but yeah, it's spiritually that's what it is. Okay, infinitesimal generator. That's what we're trying to define. But yeah, formally it's going to look like this, and I'm going to spare myself some writing and just say v, which is understood as being evaluated at t, and we're trying to take this limit.
okay.
I know that's gonna like cause you problems. But that spiritually, that's what we're doing. Morally, that's what we're doing. Okay, and so that's the solution in this case. We would use this advection equation in order to tell us how to translate our or how to manipulate our v so that it gives us the same output. But we want a more general way of doing this, and it's actually pretty straightforward. Does anyone have any ideas of what tool we could use to come up with a more general formula for an infinitesimal generator? All right, Taylor series. Okay, so with the Taylor series, if what we're trying to do is we're trying to evaluate uh, some we're trying to evaluate this expression, and we can expand this out to first order. We can write this in terms of derivatives of v, right? So to first order, I'm going to again write v to denote just the value at t. We can write v, and then to first order, we can say plus some dt times times dx dt. Oh, actually, sorry. Let's do time derivative first. So note that v is depending on time now, so we want to include a time derivative of v. So this is actually the partial derivative of v, right? So v is changing on its own accord, right? Like if we look back to this picture here, imagine that v is also kind of like changing shape with time as well, just by itself, before we consider this operation of moving the x or trying to simulate moving the x, right? Is that clear? So using chain rule, we can write this out as dx dt times partial x v. And to first order, that is our Taylor series. And again, v is understood as being, or these v and all these derivatives are understood as being evaluated at t. But this thing, dx dt, is just given by our dynamics, right? So in the general case, this is going to be some fxu t. And so if we consider, if we're trying to find what this AV is, in this case where we have deterministic ODE that is evolving our state over time, this is going to be just partial t v plus f of x u t partial xv, which is again an advection equation. So that is what A is in the deterministic case. That is what our infinitesimal generator is. It's something like that. So if we go back to the Hamilton-Jacobi-Bellman equation, when I write A, I'm saying in the case where we have an ODE, you know, whatever our ODE is, this is a very general expression for an ODE. We just plug that F in to an equation like this, and that's what our A is. And that tells us basically how is our value going, or how's our optimal cost going to change, or just how is our cost going to change under a step T, right? That this encapsulates what that change is going to be. So let's look at let us look at a very simple example. We kind of already looked at this, so maybe I'll just write it out because we're going to need it in the next step. I'm just going to write the solution because we did just look at this example. But if we have the ODE dx dt equals some constant u, or maybe even some time varying u, then the solution is for our infinitesimal generator is just going to be AV equals partial t v plus u, which, yeah, might depend on time, times partial x v. Okay. And that's going to set us up to look at a deterministic, or an example of a deterministic optimal control problem.
This U is different from U everywhere above, correct?
Oh, did I use U? No, it's the same U. So we're looking at a specific case of this function. So a case where it's just, you know, it just depends on U.
I thought until now U of t was a trajectory.
Sorry. I might have been unclear when I said that earlier. So x of t is going to be our state space trajectory. U of t, I know I've been using the term trajectory, but I just mean it's our control. I should have said that. U is our control dependent on time.
Mm-hmm.
So yeah, U is control and X is state. Okay. Sorry, I might have overloaded the term trajectory earlier. Okay, so the optimal control problem that we're going to look at is almost the simplest example that you can think of. So we're going to look at the case where we have these dynamics. So I'm not going to write them again. These are our dynamics. And then we might want to say that, you know, x of 0 is equal to some x sub 0. And then we're going to just start by looking at the case where we just have a terminal cost. So I'm going to write.
So this is the case when you're driving the golf cart and you control the velocity by pressing your accelerator pedal.
Kinda. Yeah, in a very simplified sense. Yeah. Because golf carts don't like translate, there's like 6 degrees of freedom and all that, but
Well, you drive a golf cart in a tunnel.
yeah, sure. Okay. So we're just gonna say our terminal costs. And actually I want to say capital T. Our terminal cost is going to be some coefficient, which I'm calling little c sub t, times x squared. So we just have a terminal cost that's quadratic in the state. And CT we'll say is greater than 0. We're going to want that. Okay, so in this case, our Hamilton-Jacobi-Bellman equations, and I haven't attached any other costs yet except for just the terminal costs, but we'll change that in a second. Our Hamilton-Jacobi-Bellman equations we can write as partial TV plus min over.
But the original problem asks how fast you should drive to the origin to minimize the cost.
So right now the only constraint, the only goal that we have is to just try to minimize this terminal cost. So ideally we'd want to drive to the origin. We would want our terminal state to be at the origin.
Are there any other restrictions, any other constraints?
We'll add another constraint. We'll add another constraint because you might already intuit that this is not a well-posed problem. If there's no constraint on our cost, then if there's no constraint on our costs, why not just shoot down immediately to zero and then just maintain that until the end? But there's also no reason why we can't do this either, or really any path. Well, we can't go backwards in time, but any path that takes us to zero at the end is optimal, right? This is not a well-posed problem. So yeah, okay. So now that we've already determined that, let's go ahead and immediately add a cost to our state as well. So I'm kind of overloading the term C, but hopefully that's okay with you guys. So I'm going to say some CU U squared. So I'm also going to add a quadratic cost in the state. And then this applies for all t in our interval 0 to t. Yeah. Okay. So let's look at this revised problem. So what is going to be our infinitesimal generator? Well, we found that earlier. It's just this right here. So we're going to have partial t v. So kind of show both partial t v plus u partial x v. And then we have to add to it our control dependent cost term. So plus cu u squared. And this equation is our Hamilton-Jacobi-Bellman for the deterministic case, and this has to equal 0. So I noticed that I took the minimum. I moved the minimum, or rather I took the partial TV outside the minimum, but there's no problem there because this partial TV is not going to depend on u. It's a function of x and t. It has no dependence on u.
Why do you not add the CTX squared?
We're going to use the CTX squared as our terminal condition. So in order to finish up this PDE, we're going to say that in the terminal, at the terminal time at capital T, sorry, my notation is a little bit sloppy. What I want to do is I want to call this V. I'm not particularly a fan of calling this thing V because V to me means value. But this is actually something that we want to minimize, and typically we want to maximize our volume, but this is fairly common in the literature. Yeah, so it's more, I like to call it more like an optimal cost. It's our cost when we take the optimal policy. So this is our terminal condition, and this fully defines our advection equation. And so the first question is, we want to take it's not really a question. What we want to do is we want to minimize this quantity with respect to u. Well, you might notice that we have, first degree, second degree. This is just quadratic. And so our u optimal is going to be our favorite, equation for the vertex of a parabola. So negative b over 2a, which in this case is going to be partial xv, negative partial xv over 2cu. And once we have that optimal control, we can now write this PDE not with respect to, or not including a minimum, but instead just as a good old-fashioned PDE. So, oh, sorry. That might have been confusing. We don't want this. Yes, sorry about that. I wrote the partial with respect to t twice. Okay, so we'll plug in our u star for this u here. So we're going to have negative 1 over 2cu partial x v squared. So this is a nonlinear PDE, which is, this is a very simple case, and typically the PDEs you're going to find in Hamilton-Jacobi-Bellman equation, they're going to be nonlinear PDEs, right? Because it has this quadratic term. Plus, so sorry. So we're gonna get let's see, I'll just write it out. So we're gonna have CU partial XV over 2CU squared is equal to 0. And then hopefully you can see that this takes us to partial TV minus 1 over 4 CU partial X V squared is equal to 0. Okay. So I'm just going to write out what the solution is. This is a nonlinear PDE, but given our boundary conditions, so again, this condition here, we can write out an analytical expression for this solution. You might want to try this on your own time. I think I'm going to write out some of the partial derivatives as well because we're going to need them later. But the solution for this is going to be 1 second, just gotta find, yes. Okay, our solution here is going to be CU times CT. So this is our control cost coefficient and our terminal cost coefficient. CT over T minus T plus CU multiplied by X squared. So we're trying to get to a parabolic cost in the terminal state, and we find that for every single realization of T, we're going to have a parabolic, we're going to have a quadratic function in X. But the scale of this parabola is changing as we go back in time. So the intuition there is kind of, look at the end state, you're kind of stuck. There's no more freedom to make a move. We expect that our cost is going to be narrower because I don't have any freedom, or rather, right towards the end, I could make a very large move with my control, but that's going to cost me a lot. If I'm further back, it's going to be wider. I'm going to have the ability to make a control over a long period of time and get a lower cost. So the cost is going to be steeper towards the end, but as I go further back in time, this thing's going to widen out because I have the space to make an optimal control to the end. Does that kind of work for people? Maybe a little bit of a picture. So what I'm saying is, if I'm right here at the end, I kind of have to just eat whatever cost I've accrued up to that point. I'm not going to be able to, my options are either kind of eat the cost or try to drive down towards the center. But in doing so, I'm going to eat a bigger cost with my control. But if I'm way back out here, I can take a nice gradual path. I can find this balance between the cost of the control and the cost of my terminal state. And so we're going to find that this, let's say C0 is going to be less than this, let's say CT, right? Okay. So, and also I just kind of want to look at this thing here. So we have this statement that U star is proportional to, or is the negative of the gradient essentially of V. This thing kind of looks like gradient descent, right? I'm not saying that's going to generally hold, but that's just like a nice connection. If you're thinking about optimization more generally, this is kind of like a gradient descent step. And the CU factors in because we're trying to balance we're not going to take such an aggressive step if CU is very large. We're going to take a smaller step because it's going to cost us more to make that bigger step. Okay, so this is our Vxt. We have our value function. And now, yeah, we want to use this equation for U star to find what our optimal control is. So U star is equal to negative partial x v over 2 cu. So let's evaluate partial x v. So we're just going to get 2 cu ct over ct minus t plus cu. This should be ct times x. So it's linear in x. And so we find that our control as a function of state and time. So when we have a control that's a function of both state and time, or when it's a function of state, we call this type of control a feedback control, which means I'm using knowledge of what my state is in order to determine what my control is going to be. The state appears explicitly in this equation. This doesn't matter in the deterministic case, but in real life, nothing's really deterministic. And so it's generally always better to have a feedback control than what's called a feed forward or an open loop control. This is called a feedback or a closed loop control, which means we're taking in information about our state to determine what our control should be. And so then just plugging in what we have for partial x v, we see we're going to get cancellation of 2 cu right here, and we're just going to get negative ct over ct times t minus t plus cu. So sometimes you call this coefficient the gain. This coefficient of x. And we can see that our gain is time varying. Now I want to use this control to figure out what our trajectory, our state space trajectory is actually going to be. So we have that dx dt is equal to u star xt, which is going to be equal to negative ct over t minus t plus cu times x. And we can use separation of variables to solve this ODE. I've already solved it, and I can tell you that the solution is going to be, so we're going to use our initial condition, x0, and we're going to write our state space trajectory as xt is equal to x0, which is our initial condition, times ct t minus t plus cu over ct t plus cu. Okay. And so this is just a function of time. And does anyone recognize what kind of function this is? So we have yeah, we just have, first degree in time. Any brave souls? It's a line. It's a line, right? First degree in time, no other complexities. Everything else here is just a coefficient, right? Maybe I should have said that. Everything else here is just some constant. So this is just a line. Our solution, our optimal state space trajectory is just going to be some line for some initial condition. And is it going to end exactly at 0? No, it's going to strike a balance between the terminal cost and the control cost. But it's just going to be, maybe what you might intuit as a solution from the beginning. It's just going to be a straight line. And so if it's a straight line, that tells us that our control is, if we don't write it as a feedback control, but instead just write it as a feed forward control, we know that the slope of this, or the time rate of change of x is going to be constant because it's a line. So u is just going to be a constant. And in fact, that constant is going to be ut is equal to negative ct x0 ct t plus cu. And maybe what I want to maybe what I want you to appreciate is how complex the process was to find this very simple solution, right? The solution couldn't have been any simpler. It's just a line. But in order to find that line, we had to solve a nonlinear advection equation. And that's just kind of the way it goes with Hamilton-Jacobi-Bellman. Even simple solutions require you stepping through this nonlinear PDE. Okay, so I'd like to get to the stochastic control problem. And hopefully we can get through it entirely. But let's just look at a new situation. So before we started with the ODE dx dt equals u. Now I want to make a stochastic equation. And the Hamilton-Jacobi-Bellman equation, the stochastic Hamilton-Jacobi-Bellman equation there are a lot of different stochastic processes that we can consider, but we're going to look at just a particular class of stochastic processes. And I know that probably not everyone in this room has seen stochastic processes, but so it's good that we're limiting it to just a particular case. But what we're going to look at is what is called a diffusion process. And a diffusion process, this is not a general expression, but a special case of a diffusion process is going to look something like this. And there's going to be something strange in this equation if you haven't seen stochastic differential equations, which is this term here, this dBT. So this is the differential of what is called a Brownian motion. Before we manipulate this, I just want to say we're kind of changing our Hamilton-Jacobi-Bellman equation. So before we had something like min over u of our infinitesimal generator acting on V plus some cost. But in the stochastic case, we're going to have to replace this notion of a deterministic value function with something else because we don't know what our value is going to be at the end. We had to try to turn the stochastic problem into something deterministic. And sort of the sensible thing to do is to try to minimize the expectation of our cost. So instead of talking about a V, we're kind of replacing this with the expectation given some initial condition X of some deterministic function V. Okay. So V is deterministic. The thing that is varying is our X, right? Our X is given by a stochastic process. And so what we're going to write instead is I'm just going to change this A. I'm going to write it as a script instead.
But you still want this minimum to vanish?
I still want equal 0. Yeah. Still want it to equal 0. We're trying to minimize our expected cost of our control. Okay. So I think it's worth seeing how we find the infinitesimal generator for this case where we have a stochastic process, and that might mean that we don't get through. We might have to breeze through the rest of this talk, but I think it's worth it.
Sorry, but are you still missing the constraint for this to be well-defined?
Yeah. Subject to, I'm just going to say, subject to, I'll just write VT is equal to some phi. Right.
In a sense, all of these problems is propagating value function back from the future.
Yeah, that's exactly right. Yeah. But the thing that's going to change in this case is once we add this Brownian motion, it's going to go from an advection equation to an advection diffusion equation.
Mm-hmm.
So let's see how that happens. Well, we have to make sense of this new infinitesimal generator for the stochastic process. So we're going to define this as, again, we're going to take the limit as some dt goes down to 0. But now we're going to write that expectation here. The expectation of X of V, and I'm going to write, forgive me for not explaining what this means, but Hopefully you know what I mean. Minus v over dt. This is the new infinitesimal generator. So it's something like, how is our expectation going to change in some infinitesimal step? What is going to be the change in the expectation of our cost function in for some function that we're evaluating over x and t after an infinitesimal step? How's it going to change? Okay. So let's address the elephant in the room, which is this dBt. So I told you this is the differential of a Brownian motion, and a Brownian motion is defined by just 4 rules. And we only really need to use one of them, but I'm just going to write them out for completion. So the first rule is that the Brownian motion at time equals 0 is equal to 0 almost surely. And what that means is that it's going to equal to 0 with probability 1. It doesn't mean that it has to equal 0, but just the odds that the probability that it doesn't equal 0 is a set of probability 0. So almost surely this is the case. The next thing that we want to say is that 2 increments of the Brownian motion and these things have to be ordered properly, but I'm not going to write it out for the sake of time. These things are independent random variables. So basically knowing what the difference is between the Brownian motion at one time and at a later time tells me absolutely nothing about what the difference between Brownian motion at another time and the time before that is. I don't learn anything from knowing the value of this increment before. And then the most important property for our discussion here is that BT minus BS is a random variable, and it's distributed by a normal distribution with variance equal to T minus S. So it's Gaussian distributed. And then our last property is that what's that?
Should T1 S1 and T2 S2 be strong?
Yeah, I think that's covered by the independence, right? Am I right?
You said there's some ordering you're omitting?
Oh, well, oh, yeah. Yes, you're saying that, these
Yeah,
intervals should be independent. Yeah. That, I didn't write out the ordering, but yeah, you want to order these things properly. Yeah, good catch. And then BT is going to be pathwise continuous. CONT for continuous, almost surely, again. So that means that any realization of this Brownian motion should be continuous. Just 0th order continuous. These things are almost surely never differentiable. I don't know if that was a paradox to say almost surely never, but yeah, never. Okay.
You specify some sigma in the normal distribution?
Some sigma? So the Brownian motion, so I'm going to scale it by sigma, but right now sigma's not making an appearance. This is
Oh, you'll put it by hand later on. If you
yeah. This is a fully unique thing that I've defined. So the important property here is this one for the sake of defining an infinitesimal generator. Because what that means is the expectation of some increment, right? This is an infinitesimal increment, but I'm going to write dB dt. It's an increment just like this. This has to equal 0, right? By the fact that this is 0 and by the way it's distributed, that expectation has to equal 0. And the second thing that we get from this, I mean, we could fully define all of its moments, but the only other moment that we need is its variance, which is going to equal, because we're just considering a t, this is just going to be dt, the length of that increment. These are the 2 properties that we need to find the infinitesimal generator. Okay. So again, this is or rather, where is it? This is our stochastic process that we want to find an infinitesimal generator for. So I'll write that again down here. dxt equals u dt. And I should say, like, if you want to treat these things rigorously and with the appropriate respect, you really need to take a class in stochastic differential equations. Because what I've written right here, it might look a little bit like an ODE, but there are things that work in the case of ODEs that don't work in the case of stochastic differential equations. Like I have to specify that what I mean by this is an Ito differential equation. And the reason why is I have to say I have to define the integral that I'm talking about. In the case of an ODE, it doesn't matter if I have some function and I approximate it by left-hand values and then take the limit of this sum, or if I approximate it by midpoint values and then take the limit of this sum, it'll give me the same answer. But in the case of Brownian motion, because it's so weird, because it's so irregular, these two things have different meanings. And so the case of the midpoint, that has a different name. You call it a Stratonovich differential equation. In this case, we're talking about an Ito differential equation, which means that we're looking at this left-hand sum. Doesn't matter for our analysis here. But just saying, I'm abusing SDEs right now. But that's a little bit of a sidetrack. So what we want to do is we want to find some Vx plus dxt t plus dt. And we're going to do the exact same process that we had before, find a Taylor series, except what we're going to find is because of this term right here, because this differential squared is of the same order as dt, we're going to have to take a second order Taylor series instead of just a first order Taylor series. So let's do that. So again, v, as I meant it before, times dt partial t v plus dxt partial x v. And then I'm going to take that second order term, second degree term here, and say dxt squared partial x xv. Right, so that's the second order Taylor series in the dxt term. So let's expand this out using our SDE that we have. We have v plus dt partial t v plus, just substituting in what I have, u dt plus sigma dbt partial xv plus 1/2, and I'm going to just expand out the quadratic, u squared dt squared plus 2 sigma u dbt times dt plus sigma squared dbt squared. And if we remember what the definition of our infinitesimal generator is, what we're really interested in is the expectation. So I'm going to take the expectation of this term here, right? Expectation with respect to x, initial condition x. And what I want you to notice is that some of these terms are going to go away. The expectation is linear, and expectation of dbt, because it's normally distributed with mean 0, this is just going to go to 0. Likewise, this dbt is going to go to 0. And the only term that we're left with that includes a dbt is going to be this term here. This is squared. And in expectation, what we had before is that this thing is equal to dt in expectation. Right? So what we're left with is just the terms that haven't been deleted, v plus dt, and now everything is a multiple of dt. So we have partial t v plus u partial xv plus 1/2. Sorry, there's one more term we have to delete, this thing here. We're only interested in terms that are first order in dt. So we can delete the square term as well. And then we're just left with sigma squared partial x xv. So this is our infinitesimal generator in the case of what I'm calling a steered Brownian motion, where we have some control and we're steering a Brownian motion, which is that dBt term. So this is, yeah, the infinitesimal generator v. So from adding that dBt term, the only thing that we did to change our infinitesimal generator was to add this diffusion term to it. So we turned an advection operator into an advection diffusion operator. Okay. How are we doing on time? It is 5. Do we want to take just like 8 more minutes? Is that cool? Everyone's cool with that? Okay, sweet. So let's just, I'm going to state another optimal control problem, but this one is going to be a lot simpler because we can use our previous solution to get most of the way there. So this new optimal control problem is we're going to use the new dynamics that we just investigated. dx dt is equal to u dt plus sigma dBt. We're going to have the same cost on our control. So I don't remember exactly what I used before, but something like, I don't remember what nomenclature I used before, but this is what I want to say, u squared. And then we'll have our terminal cost, which is going to be, yeah, maybe I'll say CT and then this should be X or something. Our terminal cost is going to be CT X squared. And so this is this defines our optimal control problem. So the new stochastic Hamilton-Jacobi-Bellman equation.
So now instead of driving an electric cart in a tunnel, you are driving an electric boat in a tunnel, and there are waves going back and forth.
Yeah. So
And your goal is to get to the origin.
right. And the people typically like to use the analogy instead of a boat, they like to use like drunken, right? Like you're taking a drunken walk. Some people call like the Ornstein-Uhlenbeck process, which is what this kind of looks like. They call it a drunkard's walk.
Wait, what's the drunkard who can control his speed to an extent?
Yeah.
It's not the drunkard saves.
So the problem that we're working towards is this drunken spider problem. So that's why I'm going along with what other people are calling it and calling it a drunken walk. But yeah, we're going to use our new infinitesimal generator. So we're going to have partial TV plus min over u of u partial xv plus 1/2 sigma squared, which this whole thing is sometimes called a diffusion constant, times partial x xv, and then we have to include our control cost cu u squared. Before anyone corrects me, I will make sure to include the right hand side is equal to 0, and also say that the vxt is equal to ct x squared. So this is our PDE.
Mhm.
Okay, some things to note. Again, this is a quadratic again in U. And actually this, with respect to the quadratic, this is like our C term in our quadratic. It's not going to affect where our vertex is located. It just changes the height of this parabola if we picture a parabola. So again, we're going to have that U star is equal to negative partial x of V over 2cu. Again, same thing. And what I want to do is look, the only new term that we have here is this term right here. And what we might note is before we had that v was a quadratic in x. So when I take the second derivative of v, I'm going to be left with just a constant, which means I want to find a solution, and I'm going to call it v sigma xt, that is just going to be some function of t plus our previous solution, v0 xt. With the idea being that I can cancel out that constant term by choosing the appropriate f of t. And that's not going to affect any other part because all the spatial derivatives, which are the only other terms that appear here, are going to they're not going to be affected by adding a function in time. That function in time is just going to be deleted by the operation of taking the spatial derivative, right? So I will tell you that what that term should be is okay, that f of t that I need to cancel out the second derivative is going to be 2 cu, sorry, no, don't need the 2. Don't need the 2. Instead, it's just going to be, I don't need the 2. I just need sigma squared. Natural log of a t minus t plus c. And this thing here is going to be my new value function. So what does this kind of say? Well, we should note that with this particular f of t, this f of t is going to be non-negative. And so this is always going to be greater than or equal to our previous v0 xt. And the reason why that kind of makes sense is I might have the good fortune of starting at x equals 0, at my time t equals 0. But because of the stochasticity, I very likely won't have the good function of staying at that 0. I'll likely, even if I try to exert no control, I'm going to stumble off my path. So I'm really not that fortunate for starting in v0. And my expected, or for starting at x equals 0, and my expected cost is going to be something greater than 0. When before I would just be able to deterministically move towards the end, just move along a straight line and get to the end and cash in on my cost of equal to 0 without having to exert any control. Now I'm probably going to have to exert some control to stay on that line of x equals 0. So my cost is higher. And so that's what that f of t does. But let's note something. Again, well, I don't have to rewrite it because it's right there. Our u star is equal, v itself doesn't appear in this expression. It's just partial x v. And so what that says is this f of t makes no difference about what our optimal control policy is. We're going to have the exact same optimal control policy that we had before. So whatever it was before, it's equal to, I believe this is what I had before, negative ct over ct t minus t. I hope I'm writing the same thing again. It's still the same optimal control policy. So that means given being in state X, I'm going to move towards the origin with this gain, with this strength. It's the exact same control policy. So, okay, that's the solution to that control problem. It doesn't make so much sense to talk about a feed forward control because feed forward controls in the case of stochasticity are not going to perform well. Right? Because that means I'm not gonna know what my state is at time t equals something other than 0. But I'm still going to act as if I were on that deterministic trajectory, and that's not a good policy. What you want to make use of the information about what your state actually is. So here's a case where the feedback and the feed forward controls yield different results. So I think with that said, I just want to show some results of some simulations. So this is on the left, we have our deterministic case. On the right, we have the stochastic case. And these lines that we see here are going to be those deterministic trajectories that we take through space. On the bottom here, these are just our control variables, which you see are just flat in time for the deterministic case. And this red curve here, that's showing the gain. So it's that part of the control that isn't dependent on the state. It's the coefficient that depends on time of the state. It's not so meaningful in this picture here, but if we look at the case where we have stochasticity added, and here I think I use like sigma equal to 2 or something like that. And then I have the Julia code. I can tell you what the CT and the CU are, but I don't remember off the top of my head. If we look at this picture here, these are the deterministic trajectories, and we have some stochastic trajectories. And what you would expect is in expectation. So, okay, let me tell you what the colors are. What I've done is I've taken the terminal cost, and then I've added the control cost backwards in time along this trajectory. So by the end, this is going to tell you this should match. In the deterministic case, it does. I mean, I've changed the opacity here, but in the deterministic case, the value at the end of this line matches what my cost function is, my optimal cost function is at that point. That's what's plotted as a heat map underneath this is the optimal cost function. And it's purple here, it matches purple. And every point along this line, it should match. But here, what you'll have is with the stochastic case, and this is the value function with that log term that we found added to it, which is why it looks different on the right side versus the left side. In some cases, it does match. In other cases, it doesn't match. It should match an expectation, but individual realizations are not going to achieve that expected value that we initially calculated. They're going to achieve their own value, but that value is a random variable. So it only matches an expectation. But if I took a bunch of trajectories and I average them together, then this should match. And we see here, again, these are the deterministic controls. But if we look at the stochastic controls, they vary a lot. And in particular, as we get towards the end here, those trajectories that have strayed far off the, where we anticipated they would go, they are seeing very large controls trying to pull them back towards center, which is what our gain policy is telling us. It says as we get closer to that endpoint, to that terminal condition, we're going to exert more and more control and try to pull us strongly back to center. And that's just the outcome of this balance between the control cost and the terminal cost that determines this. And that's pretty much all I have for this week. If you have any questions about this, please ask. But in next week, what we're going to look at is we're going to look at a little bit more complicated case. We're going to try to approximate this drunken spider problem, looking at this Kaplan paper. So if you want to, read it beforehand and try to get an understanding of it, it's more complicated, a lot more complicated than what we talked about here today. This is kind of just laying the groundwork for the more complex stochastic control problems. But we're going to be looking next week at the case where instead of having this unimpeded, there's no penalty on being in a particular state in the domain of But next week, we're going to look at the case where we have some high penalty, actually an infinite penalty of being in some particular region at some period of time, which is meant to approximate this drunken spider problem where if I land in the lake, it's game over. Okay. So yeah, if you have any questions, if you'd like me to share the spaghetti code for these Julia plots, I'd be happy to do so. Hopefully next week, yeah, maybe have some more materials prepared. But yeah, and also if this was too basic, you can let me know that too. But I think next week will be more complex. So yeah, questions online or questions in the room, I'd be happy to take them.